So far, we have focused our attention on a time correlated single photon counting, which allows us to make measurements of lifetime from hundreds of picoseconds, well maybe tens of picoseconds if you can have a very good instrument like we do, and up to say hundreds of nanoseconds. In some cases, you might be able to go beyond that as well. Today, we talk about a technique which allows you to go down further to hundreds of picoseconds at least, if not better. And this technique is called time resolved fluorescence upconversion, or the name I like better is femtosecond optical gating. The reason why I do not like the term fluorescence upconversion is that there are many people working in the area of material science who want to make upconversion materials, materials in which like 2 photons of smaller energy would join up to give you 1 photon of higher energy, and the moment they see fluorescence upconversion technique, they come and ask me, is it possible for us to test our samples on your equipment? Of course, it is not possible to test their sample on our equipment. So, I like femtosecond optical gating better just to avoid trouble, but then fluorescence upconversion technique is an absolutely valid commonly used name, and we will see where this term upconversion comes from in this technique and how is it that we get accuracy in time up to femtosecond scale. Before proceeding further, it is important to point out that none of these slides are made by me. I do not know how to make such beautiful slides. They are all prepared by my colleague Professor Shobhan Sen from School of Physical Sciences, Jawaharlal Nehru University. He has kindly agreed to allow me to use these slides as many times as I want, wherever I want. So, let me start thanking Shobhan for these slides that are made with a lot of care, as you will see. So, first of all, let me show you a photograph of the upconversion spectrometer. This is what it looks like. This is actually a photograph taken from top. This is not our instrument, it is the instrument that is there in JNU, but then our instrument is pretty much the same. And next day we are going to go to the lab and we are going to show you our instrument in real time, and we will show you how the data is recorded. So, the idea is in this module we are going to tell you and try to make you understand without actually going to the lab how the data is recorded and what are the underlying principles and all, and next day you will come to the lab and you will see what exactly is actually done, right. So, what you see here is this black flat surface with a lot of holes is a breadboard, and if you go to any optics lab you will see breadboard like this. In fact, if you look carefully you will see that this black surface with holes is sitting on a shiny surface with holes. That is an optical table, the top of the optical table, and the reason why we have so many screws, so many holes there is that it is possible to use bolts and screws and fix pieces of optics on this surface. Now, whatever you see here is a piece of optics. It may not be very clear from this photograph because it might be for many of us that we are seeing such apparatus for the first time. But when we go to the lab and we see everything in front of our eyes, I hope it will become clear, and today's exercise is going to help us understand things that are there as well. So, to start with, let me try to give you from this figure a description of what is there in the spectrometer. So, first thing that you have is what is written as SHG crystal. SHG means second harmonic generation crystal. We are going to have a couple of modules on nonlinear optics later on, and there we will learn that there are materials that allow 2 photons of they may be same energy, they may be different energy, but they allow 2 photons to combine and produce a photon of larger energy. It is pretty much like 2 drops of water falling on a table coming together and forming a bigger drop. It is just that the drops here are not drops of water, they are drops of energy, drops of light. But not everything allows combination of photons. There are very stringent conditions that have to be satisfied for a material to act as a nonlinear optical material, and that in itself is a very active field of research. So, without going into that at this time, just believe me when I say that the first thing we have here is a second harmonic generation crystal. What is the purpose? We will see in a while. Now, why are we saying second harmonic? Because in this crystal at least what happens is you make incident laser light nominally of 800 nanometer, but whatever laser light you might want to use, and two photons of the same laser join up to produce a photon of double the energy. This photon of double the energy, that is called second harmonic. Or if I put it in another way, suppose the frequency of the incident light is omega, then two photons of frequency omega join up to produce another photon of 2 omega. This 2 omega is a second harmonic of omega. It is as simple as that. So, what we do here is that you make incident this red light, which is from a laser. In our case, it is a femtosecond pulsed titanium sapphire laser. Later on, we will have occasion to talk a little more about what is there in the laser and how femtosecond pulses are produced. For now, let us just accept that this red light is the output of a femtosecond pulsed second harmonic, femtosecond pulse titanium sapphire laser. And wavelength of this laser, that the one that we have, can be tuned from say 700 nanometer to 1000 nanometer or so. Let us say that this red light that we are showing you here is has a wavelength of 800 nanometer. Okay. Of course, if I say wavelength of 800 nanometer, it is not very difficult for you to work out what the frequency is, because frequency and wavelength are related by lambda nu equal to c. Okay. Now, what happens in the second harmonic generation crystal is that, as I said, two photons join up to give you one photon. So, suppose I am using 800 nanometer light. What will be the wavelength of the some frequency photon? This one is very easy, it is going to be half, right, 800 by 2, 400. But while doing this thing, please remember one thing, that you have to add frequencies, not wavelength. Wavelength is actually in reciprocal scale. So, the right way of doing it is to convert whatever you have to frequency, add the frequencies and then go ahead. You will see when we talk about some frequency generation later on, rather than second harmonic generation, that will become a little important. Second harmonic generation is easy, because the wavelength of the output is just half of the wavelength of input light. Okay. Now, here let me tell you something, it is a little easier to produce second harmonic of femtosecond pulse laser, short pulse lasers. Why? Because when you do second harmonic generation, what are you doing? The first photon takes the material from its ground state to what is called a virtual state. A virtual state is a non-stationary state associated with a lifetime of 0, and it is usually described as a linear combination of the stationary states of the system. So, requirement for second harmonic generation is that you take the system from the ground state to the first stationary state, then there must be another photon of the same energy which will take it to another virtual state. Okay. So, first frequency takes it to an energy of say nu, well I am stating energy in terms of frequency here, omega. Second one, second photon also of omega frequency takes it to a virtual state whose energy gap between whose energy gap with the ground state is equivalent to a frequency of 2 omega. And now there is no memory, the system does not remember that it had gone up in 2 steps, and it cannot stay in virtual state for any finite amount of time. So, it has to emit a photon and comes down, and since the energy gap between that virtual state and the ground state is equivalent to frequency of 2 omega, it actually emits a photon of 2 omega, and that is what you see as the sum frequency, or in this case second harmonic. It may be a little difficult to follow it in this way when I speak, but then later on when we talk about nonlinear optics, we will actually draw diagrams, and then I hope it will become a little easier. For now, all we need to understand is that this red light falls on the second harmonic generation crystal, SHG crystal, and blue light is produced. And what you have seen is the path of the blue light. I will go back a little and I will show you the path of the blue light, but before that let me tell you, you could see what happened, right. Blue light gets produced here at the second harmonic generation crystal. It hits, what we have here is a dichroic beam splitter. Dichroic beam splitter means it reflects one color and transmits another color. In this case, you use a dichroic beam splitter which reflects blue light, but transmits red light. It could be the other way around as well. You have dichroic beam splitters of both the variety. Then, having been reflected from this dichroic beam splitter, the blue light comes to another dichroic beam splitter. This one dumps the residual red light. Residual red light goes through and blue light gets reflected in this way, where it gets focused on the sample which is kept here by a mirror, by a lens, alright. That is the path of blue light. I will just show you the animation once more. Blue light is produced at second harmonic generation crystal, hits the first beam splitter, second one, and now is focused onto the sample using a lens. In our case, we use a lens, but there is a better option as we will come to later on. Now, then the sample fluoresces, and this is why you need blue light. As we have discussed in one of the first modules, fluorescence spectrum always comes at a lower energy compared to the excitation light, unless you have an upconversion material, right. But normally when you talk about normal fluorescence, emission always has emission is always at a lower energy, because you cannot have more energy than what you put in, unless something like this is going on. That is why you need blue light, because suppose you excite using 800 nanometer light, where is it going to emit? The only hope is NIR. In fact, materials emitting NIR are very useful, but most of the things actually emit in visible range, sometimes in UV range. So, for that you need higher energy light, and that is what is produced by this second harmonic generation crystal. So, red light, second harmonic generation crystal gives rise to blue light that is deflected through a lens onto the sample, and then from the sample you get fluorescence that is shown by this line. Now, fluorescence occurs in all directions. So, fluorescent light is sort of like the light that comes out of the regular lamps that we have. It is in all directions, and what we do here is that we collect the fluorescence by using this lens. So, you can understand this is the sample, this is the lens. So, the only fluorescence it can collect is something that comes from this point on the sample on which the excitation light has been focused and is within this solid angle that can be captured by the lens. So, here something that becomes very important is numerical aperture, okay, ratio between the focal length of the lens and the diameter of the lens. If your focal length is large, in this case, is it good or is it bad? Do I want to use a large focal length lens or a small focal length lens? Definitely small focal length lens. In fact, there are instruments in which they use a microscope objective. You want the lens to be as close to the sample as possible, because the further away you go, more is the loss of light. If you are here, then you are catching, say, this solid angle. If this is, suppose this is your lens, cross section of your lens, you keep it here, this is the solid angle that you catch. You go here, this line goes in this direction, this ray goes in this direction. So, you end up catching a much smaller solid angle, right. That means light collection is less efficient, and fluorescence, in any case, the number of photons emitted is not all that great, especially when you are talking about femtosecond time scale, your lifetime is small. And what we learned in the previous module is that lifetime is proportional to the fluorescence intensity, phi f is equal to kr into tau f. So, small lifetime would usually imply a small quantum yield as well. Now, out of that, if you are going to reject most of it, then what will you see? So, that is why you want to capture as much of the solid angle as possible. If you can capture 360 is never possible. If you could capture 180 degrees, it would be great, but 180 is not possible. So, you want a lens with high numerical aperture, so that you can go as close as possible and capture as much of the fluorescence light as possible. Are we clear about that? Okay. And the other thing that is also implicit here is that the sample is kept at the focus of the collecting lens. That is the configuration for best collection. So, you told me you do not want a long focal length lens, and we discussed why. Do you want a small wider lens or do you want a narrower lens? I mean diameter of the actual optic. Should it be small, should it be large? It should actually be as large as possible, but there is a practical problem to that, because your focal length is small. If you want a very large lens, then it is going to be a very huge curved surface like that, it cannot be very large actually, right. So, there is a limitation, that is why numerical aperture is the quantity that determines what kind of lens you are going to use. Alright. So, let us see what is happening here. We have some labels here. Omega 2 is the frequency of fluorescence as we are denoting here. What is omega 1? We will come to that shortly. So, this fluorescent light is captured by the lens with small focal length. Then here we have a filter. What is the purpose of this filter? You see, you are doing a collinear collection. You are collecting in the same direction as the direction of propagation of the incident light. So, of course, there will be not only this fluorescence light, a lot of excitation light will also be there in the same path, but then you do not want it, right, because if excitation light gets into the detection channel, then your instrument is going to get messed up. So, you want to cut out an excitation light, cut out the excitation light, and you want only the fluorescence light to reach wherever it is going to reach later. So, now tell me, how do I cut out the excitation light and allow only fluorescence to go through? What should I use? We should use a filter, that is right. What kind of a filter? A filter that cuts out high frequency, high energy, short wavelength light and transmits low frequency, low energy, long wavelength light. What is that kind of a filter called? It is called a long pass filter, that is right. So, in equipment like this, you have to actually use many different kinds of filters. Here, you use a long pass filter, and the purpose of that filter is to cut the excitation light while allowing the fluorescence to go through. Here, if you look carefully, you will see there is another something. Here also you have some filters. These are a different kind of filter. They are called neutral density filter. What is the meaning of a neutral density filter? Something that ideally cuts down a lot of the light going through irrespective of wavelength. So, if you plot absorbance or rather percentage transmittance against wavelength, then you expect to see a flat line in case of neutral density filters, a flat line that is at 50%, 20%, 10%, 1% depending on your need. Why do we have neutral density filters here? Because we do not want too much of light to fall on the sample. You are using a 100 femtosecond pulse. So, that is putting a lot of energy into the sample in a very, very small time. So, sample is going to burn. That is why you always want to work at minimum excitation energy possible. If you put in more excitation energy, perhaps you will get stronger fluorescence, but that comes at a cost, and the cost is your sample might get damaged. And if you are not careful, you might not even understand that your sample is getting damaged. So, the problem with that is that once we are done with this discussion, we can come back to it. The problem with that is that you actually get incorrect result. The lifetime you record can actually be different from what it is. That problem is not there in TCSPC. In TCSPC, first of all, not much of damage is there if you use diode lasers and all. Secondly, it does not matter if the sample degrades even during the experiment. Unless another fluorescent species is produced, lifetime will remain unaffected. Not so in upconversion, not so in optical gating. In this case, if the sample degrades, even if it becomes something that is not fluorescent, then your measurement can be affected, and we will discuss why once we are done with the remaining part of the experiment of the discussion. All right. So, what do we have? we have this fluorescence going through the long pass filter, then that cuts out all the blue light, only fluorescence light goes through. Here you have a lens. Perhaps you will understand better when we show it to you in 3 dimensions next day. Here you have a lens, and this lens focuses the fluorescence light onto another nonlinear crystal, but here you see this one was SHG crystal, the first one, the second one is called SFG crystal, because here it means some frequency generation crystal, not second harmonic generation crystal. Why do we need a nonlinear crystal? What is it doing there? What is the function? How does it help? We will come to that shortly. But for now, we need to remember that this is a some frequency generation crystal. Now, you see here when I say long pass filter, you might actually have to use a different filter for a different sample. That is why in this kind of an instrument, you always need a set of filters. What you see here, you can see some color there, they are all colored glass. A set of filter, mostly long pass, which allow only the fluorescence light to go through, but actually not all are long pass, some short pass filters are also there, we will come to that, alright. So, are we all okay with this path? Fundamental red light getting frequency double, producing blue light, which is directed onto the sample, focused onto the sample, then fluorescence light goes through a long pass filter, whereby the excitation light is eliminated, and then the fluorescence is focused by a lens onto a some frequency generation crystal. Are we okay with this arm? But this is only one arm of the instrument, only half of the story. The remaining half of the story, and that is where omega 1 comes in, is in this side. Remember, what is this optic here? Is it a plain, is it a simple mirror? It is actually a dichroic, right, and dichroic reflects blue light and transmits red light. So, what you see now is the path of the red light, which is omega 1. I will show you the animation once again, but then I am afraid I cannot speak fast enough to keep up with the animation. After all, we are trying to animate light, which is the fastest thing in the universe. So, let us see. So, red light goes through the dichroic, hits a mirror, another mirror, goes to a retroreflector, comes back, see, I could not keep up with it. So, now let me try to do it in a static mode. So, this is where your red light goes through. Where is it produced? It is produced in the laser outside the spectrometer. It is there. If you see carefully, you can see 2 beams, one blue and one red. So, that red light goes through the dichroic, hits this mirror, then this mirror, comes back, and here you have a retroreflector. Retroreflector means it can even be a pair of mirrors, something that turns light back. Okay? Light does an about turn at the retroreflector. What we have in our lab and in these instruments which are marketed by CDP Corporation, what they always have is they have 3 sides of a cube front coated with gold. There are some advantage with having 3 sides of a cube. The advantage is that the light that comes out from the retroreflector is exactly parallel to the light that goes in. That helps in alignment. So, if light goes in like this, it will come out like this. If it goes in like this, it will come out like this. So, having a retroreflector which is 3 sides of a cube helps us in the alignment a little bit. But after that, again you have another mirror which takes the light to this mirror, which focuses it through the same lens onto the some frequency generation crystal. And we are saying that this red light has a frequency of omega 1, okay, and this light also goes by the name of gate light. Remember, one of the names is femtosecond optical gating. This omega 1 serves as the gate. Before going any further, let us make sure that we have not forgotten what kind of a light is that red light. Is it continuous wave light or is it pulse light? It is pulse light, right, where remember it is the output of a femtosecond pulse titanium sapphire laser. It is pulse light, full width and half maximum of the pulse would be something like 100 femtosecond in our case. it can be even smaller, okay, pulsed light. Omega 1 is pulsed. So, what does it look like if the x axis is time? It looks something like this. What about omega 2? If I look at it in time domain, what is the time evolution of omega 2? It is from fluorescence, right. So, it is a decay, okay. This is a point that we are going to come back to shortly, right. But before that, let us think in a little simple manner, not worrying about time at the moment. Now, you see what we have done. We have focused light of two different frequencies, omega 1 and omega 2, onto the some frequency generation crystal. What should happen? It is a nonlinear crystal, it is called a some frequency generation crystal. So, it would better give rise to some frequency. What is the meaning of some frequency? Omega 1 plus omega 2, alright. So, this some frequency is generated here, and actually it is this some frequency that is detected. How do we ensure that? After here, what we have not shown is we have a monochromator like the ones that we have discussed earlier while talking about steady state measurement, but generally here you use a double monochromator. There are two gratings because you need very high precision in this case. And then you have a regular photomultiplier tube or some other photodiode detector like what you have in your say a fluorescence spectrometer, okay. So, you are going to see omega 1 plus omega 2, and if you just measure the photocurrent out of the photomultiplier tube, then you can get an idea about the intensity of the some frequency omega 1 plus omega 2. Are we clear? But what does all this have to do with femtosecond time resolution? So, femtosecond optical gating, we have understood the optical gating part perhaps because we said that this omega 1 light is called optical gate, but why is it called a gate? And we have understood the femtosecond upconversion because here we are doing upconversion. So, this crystal is also called the upconversion crystal, okay. But how does that give us femtosecond time resolution? That is what we are going to discuss in the next module. Before that, let us do simple arithmetic. I have 800 nanometer light, right, that is omega 1, okay, and 600 nanometer light. Here of course fluorescence is broadband. Let us say we are focusing on the 600 nanometer fluorescence light, okay. So, what wavelength is obtained upon mixing 600 nanometer and 800 nanometer light? Well, what I have written is 800 nanometer and 600 nanometer light. Can we work it out? Of course, maybe I can do a little bit of mental arithmetic. It is upconversion, right. So, you have to add 600 plus 800, 1400 nanometer is the wavelength of the, are we going to get 1400 nanometer when we combine 600 and 800 nanometer light in some frequency generation crystal? Why not? Because see 1400 nanometer is actually lesser energy than both 600 and 800, right. And let us not forget that when you add, so go back to the fusion of drops analogy. When two drops fuse, two drops of water, their masses add up. When two drops of light, when two photons fuse, their energies should add up, right. E equal to h nu or E equal to h c by lambda. So, what you need to do is E1 plus E2, you cannot do lambda 1 plus lambda 2, right. So, E1 plus E2 would be h c 1 by lambda 1 plus 1 by lambda 2. So, lambdas are, you cannot add lambdas just like that, you have to add frequencies. So, who can tell me what is the wavelength we will obtain when we mix 800 nanometer with 600 nanometer? You have to work it out. I do not think you are so good at mental arithmetic that you will be able to do it just like that. I am not. So, what you actually have to use is 1 by lambda equal to 1 by lambda 1 plus 1 by lambda. So, if you do not believe in taking LCM and all, it is 600 plus 800 divided by 600 into 800, but reciprocal of that. It turns out to be 344 nanometer. Now, tell me this 344 nanometer light, is it UV, is it visible, is it ultraviolet, is it infrared, what is it? UV, right. So, now suppose your 800 nanometer is the nominal value for omega 1, if omega 2 is less than 600 nanometer, it will be even more higher energy, some frequency will have even higher energy, more into UV. What is the best case scenario? If this is 800, the second one can be at most 800, actually it cannot, it has to be longer than 800 nanometer, right. So, if it is 800 nanometer, no, what am I saying? It can be anything actually, because you are exciting by 400 nanometer, sorry sir, my mistake. But suppose it is 800 nanometer, then it will be 400. So, typically, well, the point I am trying to drive at is that now when you choose the monochromator and you choose the detector, you want a monochromator and a detector that work well in the ultraviolet range. We have not had the scope of discussing the blazing of monochromators, unless you are using monochromators that use your holographic grating, they are usually blazed at some wavelength or the other. That means, they are optimized, the performance is best at that wavelength. So, if you have a grating that is blazed at 600 nanometer, that means you will get maximum light coupling at 600 nanometer. If you have something that is blazed at 300 nanometer, that is what it means. Okay. So, typically, and same is true for detectors, and you do not have one ring to rule them all usually. So, you have a detector that works well in a particular range. So, when you do the upconversion measurement, you might think that you need a rate sensitive detector, you do not, because you are looking at some frequency, higher energy. You will always need a higher energy, you will need a detector that works well in UV region. So, that is another point to remember, that you are actually detecting UV. So, your instrument would better be such that it can detect UV nicely. Okay. But we have still not answered the question, where is femtosecond in all this? Where is the question of gating? That is what we want to do in the next module, when instead of using the photograph, we are going to use the schematic, and we will show you where femtosecond time resolution comes from.